Right, everyone. Welcome back to this afternoon session. We got a bit of a change in topic this afternoon. We're going to be talking about the ISM and star and planet formation. And our first speaker is Noé Brucy, who will tell us about what regulates star formation, a two-scale approach to explain the Schmidt-Kennicut relation. I will give you, like Adrienne did this morning, a verbal 3-minute warning when you've got 3 minutes left. So off you go.
Thank you. Thank you everyone for being here online. So I would present the work I've been doing during my PhD under the supervision of Patrick and Bell on the regulation of star formation, and especially how we can use both the kiloparsec scale and galactic scale simulation to try to get a better understanding of the Schmidt-Kennicut relation. So if we just consider a very simple model of star formation, you can just consider that star formation occurs when a massive cloud of molecular gas collapses under its own gravity and then forms stars. And if you want to get a rough estimate of how much star you form by unit of time with this process, with only gravity considered, you would divide the mass available in the cloud by the free fall time, so the time needed for the gas to collapse. And you will end up, if you take parameters for the Milky Way, for example, with a star formation rate, so the amount of star you form by unit of time, of a few hundreds of solar masses per year, which is way above what you can observe in real life. Meaning that there are obviously other processes than gravity that quench star formation, that will act against gravity and stop the gas from collapsing. And it occurs that even with these quenching processes, there is still a strong relationship between the amount of gas available and the star formation rate. So this is the Schmidt-Kennicut law that links the Coulomb density of gas in several galaxies. So each dot represents a galaxy, with the surface density of star formation rate. If we, so in this study, I will focus on this range of galaxies, so starting for Milky Way-like galaxies up to galaxies that have Coulomb density about 10 times higher than the Milky Way. And the goal is to try to understand what are processes that explain the Schmidt-Kennicut law, that shapes the Schmidt-Kennicut law. What are the main processes that stop star formation?
Noé?
Yes?
So, something has changed in your microphone. Your
I'm very
voice
quiet.
is very low. Yeah.
Is that better?
Yeah.
Okay, sorry. So where we're at, yes. And to try to get a better understanding of the Schmidt-Kennicut law for this range of galaxies.
Sorry, it's happened again. We can barely hear you.
Why it is so, I don't know. I will try to check this. We ran a numerical simulation in, I don't understand, he's still doing this. Okay. In both at the kiloparsec scale and the galactic scale. So my my setup is the following. The first setup I will use is the kiloparsec scale. I don't know. I can understand. Okay. Just make me a sign if you do it again. It's a
wait a moment. Let's try to fix that. I think the reason is that in your microphone settings, you have automatic adjustment of the volume of the microphone. So try to click that off, and the sound will be stable. I think. Try this. You have a little arrow next to microphone, audio parameters, and then for the microphone, ajuster automatiquement volume du micro in French.
You
click out.
Audio. Okay, yes, it was there.
This will be stable.
Okay, yeah, okay. The automatic adjustment is not so clear, visibly. Okay, is the sound good now? Okay, I'm sorry for that. Thank you again. So yeah, and the advantages of running such just a restricted zone of the galaxy is that we can have a fair distant resolution of 4 parsec everywhere. We can even do more. We can run several simulations with different parameters and explore the parameter space. Yes. So we use the Ramses ISM version with the cooling function that represents the cooling of the ISM that was developed by Patrick and Bell. And star formation occurs when the density reaches a given threshold. And when this is the case, we have a string particle that will create all the gas over the threshold. And at some point, it will create a stellar particle on which will be, and that stellar particle representing an individual star, which then emits feedback. We start with a stratified disk with a Gaussian profile with this midplane density that we can change to change the column density. There is also a stellar and dark matter potential, which is kept the same for all simulation, whatever the column density is, and an initial magnetic field, which is first aligned with the x direction and which is also Gaussian. The boundary conditions are periodic in the midplane and open in the vertical direction. So feedback is done via photoionization. So we have H2 region around the string particle. It is computed via rotative transfer. We also have feedback from the far UV that can go through the nearby gas and heat up regions that are far away from the stars. And to model this, we have a very simple model where we apply a uniform background heating, which is taken to be proportional to the star formation rate, because it's mainly the massive stars that produce this far UV feedback. And then the stars can, at the end of the life, the star explode and inject energy back into the stellar medium into the form of momentum, representing the supernovae. So this is what it looks like for a column density of about 40 solar masses per parsec square. So you see that on the left, you have the column density, on the right is the midplane density. You see that we start to form stars and accrete through big filaments that go into big clusters, and you see the effect of the feedback that sweep up the nearby gas, but at larger scale, you still continue to accrete and form big clusters. So we can look at the column density for several initial column densities. You see that at for each simulation, we will form these big clusters. Indeed, when we increase the column density, we will have more flows due to the feedbacks, but also bigger clusters. We can then try to measure the star formation rate by looking at the mass that has been accreted within the things. So this is the solid lines for each simulation for different column densities. And we compare it to the mass, in the stellar mass we can expect if the star formation rate was constant and equal to the to one given by the Schmidt-Kennebec law. That is the dotted lines. So you see that for galaxies that are a little bit more massive than the Milky Way, at about 13 solar masses per parsec square, we are pretty close to the Schmidt-Kennebec rate. But if we go to higher column density, we completely overshoot and we form very, very many stars. And we can average this curve to get the star formation rate and at the end get a star formation law for this set of simulations. And we see that the slope we get is power law of power with an index 2.5, much higher than the 1.4 for the Schmidt-Kinniget law. We are pretty okay for Milky Way-like galaxy, but as soon as we go to gas-rich galaxy, the discrepancy is very high. So that means that we are missing a very important process that will quench star formation, at least for these galaxies. So one possibility is that because we only simulate the origin of the galaxy, we are missing all the large-scale dynamics of the galaxy, such as perturbation that creates spiral arms, but also the turbulence due to the angular momentum transport when we have a radial mass transfer. That you can also imagine like only the shear created by differential rotations or accretion from outside the galaxy. All these processes are expected to create turbulence at the kiloparsec scales, and this turbulence will be mainly bidimensional due to the disky nature of the galaxy. We can have a worth estimate of the injected power. So by mainly by assuming that the tumor parameter is constant and equal to 1, and since we keep the same stellar content, we can expect that the epicyclic frequency is also constant. So at the end, we can have an estimation of the power injected that scales as a Coulomb density to the power 4. Now, in Ramses, if we want to mimic this turbulent driving at the kiloparsec scale, we can use the turbulence module that has been recently merged with the main Ramses version. That, thanks to the work of Tine Coleman, thanks to so that will generate 2D an extra 2D force at scales between 300 and parsecs and 1 kiloparsec. So then the idea is that we just use a parameter in the formulation of the driving to increase the strength of the driving as a function of the Coulomb density. And I've run 2 sets of simulations, one medium driving that scales as a Coulomb density to the power 2.5, and one strong driving that scales as a Coulomb density to the power 3.8. And the outcome is quite different, especially if you look at the movie. You see that now the main the dynamics dominated by this turbulent driving, and we still form stars. We will see in a few moments, and we still have feedback at lower scales, but we have like bigger scale structures that create less. We have not these clusters that we had before. So we can compare the Coulomb density maps for the different kind of driving. So no driving at all, that's the feedback only simulation we had before, medium driving and strong driving. And you see that, and if you go from left to right, you increase the Coulomb density. And you see that the more you have driving, the bigger are the structures, and the less you have, you have less star clusters. And that can be verified if you look at the mass within the things. So now we have we create less stars, and we are closer to the rates given by the Schmidt-Kinniget law, and that can be verified if we do as an average. So with the medium and the strong driving, we are closer to the Schmidt-Kinniget law.
No, wait, 3 minutes left.
Yeah. Okay. So that doesn't mean that the turbulent driving from large scale is the only solution, but that means that it may explain why there is such a difference between what we see in our feedback only difference, our feedback only simulation, and the Schmidt-Kinniget law. So as I said, the cool thing with this kiloparsec scale setup is that we can run a lot of them, experience have tweak the parameter of the turbulence, for example, change the compressibility, the strength, etc., in order to test different setups. but it's also a caveat because we don't simulate the turbulence depth consistently. So what we would like is to know whether the strength or the nature of the turbulence we have in our kiloparsec cube box is realistic. At least it is comparable to what we have in observations. The thing is that we don't have a lot of observations of such gas-rich galaxies that have a really detailed view of the velocity field. So in order to have better constraint on the large-scale turbulence, I've run galactic scale simulations that are still running and still being analyzed. And the idea is to use the simulations to measure the star formation rate to verify if we still have the Schmidt-Pinniget law, but also the velocity dispersion at the kiloparsec scale. So we extract kiloparsec box from the big simulation and we compare to the previous simulations, and also do more statistical measurements such as the power spectrums and see how the energy move from the different fields, from dark matter to stars to gas, etc. And yeah, and so this I let you with my takeaway slide. And so the idea will be really to compare what happens at the kiloparsec scale in these simulations to see if we can retrieve the result we had in our box simulations. Thank you for listening.
Thank you for your talk. We got one question already, so I will immediately pass over to Eric. We can't hear you. No, it's very, very faint. Your microphone must be very quiet.
I'm not the only one with my problems. I don't.
Better, but still very quiet.
Okay.
Now we're good.
Better.
Yeah. Okay, let's try like that. Sorry. Yeah, I was saying very interesting talk. Thanks a lot. It's indeed not very easy to guess what kind of turbulence you get in. I have a question, which is when you looked at the potential constraints from observations, there is a recent paper by Jonathan Enshow, sorry, that shows that there are some very interesting scales that may be related to the driving of turbulence, looking at basically position velocity of the dense gas, CO. I don't know if you're aware of this and if you have looked at that.
No, I think I will be really interested to look at this if you can send me the reference.
Yeah, I'll send you the link via Slack.
Yeah, I'm craving for such a constraint.
So the other related question was, do you already have some when you set up the turbulence? I'm not aware of this module, but is it how is it set up? Is it the 1/3, 2/3 standard solineal compressive? How does it work?
We can, in fact, we can choose the compressibility, the solenoidal fraction of the turbulence we have. So in this run, we found out when we set up the turbulence, the goal was to see whether it was possible to get this match with the Schmidt-Pinniget law. So we found out, and that's also a figure I have somewhere, yes, that more solenoidal modes were more efficient at killing star formation. So I think for this run, the solenoid fraction is of 75%, and that's something that also be found in galactic scale simulations. But that's also something we want to have a better constraint on. For now, it's mainly solenoidal turbulence, but we can also have more compressive one.
Thanks.
I think we have time for one more quick question. So Tawa, go ahead.
Thank you for nice talks. If I remember correctly, your star formation scheme is density-based. So yes. I wonder if the driving of the turbulence can reduce some dense regions in the simulations. So it depends on the mode of the turbulence. The complex can make some dense regions, but the solenoids do not. So I wonder the driver of turbulence can change the density PDF in your, how can change your density PDF?
I don't have the plot right now. I think, yeah, indeed, the what you expect is that whatever the turbulence you have, if it's bit compressive or solenoidal, since you are reducing the star formation rate, you will move the PDF to the left. I mean, you will have we will reduce the dense part of the PDF. But I don't have the precise plot right here. I think that that's something we are looking at, but yeah, I cannot say more than that.
Is there any ballistic convergent criteria for star formation scheme?
No, the star formation is very simple. It's just if we go over the density threshold, we put the mass into the thing. Okay. We expect that at some point, if we are dense enough, the mass will eventually be converted in star. So it's at lower scale, so we don't really track this. Okay, this is tracked by the same particle.
Okay, so I think it's time to move on. So can our next speaker please start sharing her screen? Asiyeh, are you? Yep.
Can you see the screen?
Yep, that looks great. Okay, so our next talk is about the second generation star formation in global clusters of different masses, brought to us by Asiyeh Yaghoobi. I'll also give you a 3-minute warning. So off you go.
Thank you. Hello, everyone. My name is Asiyeh Yaghoobi. I'm a PhD student in IASBS in Iran. Thanks to the organizers for managing this meeting. And as you can see on the screen, I would like to talk about second generation star formation global cluster of different masses, which is the result of the study working on it with my supervisor. So, you know, global clusters were traditionally known as a simple stellar population, means all stars in a cluster share the same age, the same chemical composition, and with different masses. And of course, we can fit only one isochron to their data current magnitude diagram. But in the past several years, so high precision observation have shown that it's not actually true. And so we know that nearly all global clusters are composed of at least 2 stellar population with different chemical composition, as you can see here. So the population with normal chemical composition is referred to first population or first generation, or FG in my talk, and the other population that shows anomalous in the light elements like sodium, magnesium, aluminum, and so on, is referred to second population or second generation, or SG in my talk. Just say that. So second generation stars show enrichment in some elements like helium, sodium, nitrogen, aluminum, as you can see here, and show some depletion in some other elements like oxygen and magnesium, for example, but with no spread in the iron abundance for most of global cluster. So these different populations are placed on the different isochron, as you can see here for NGC 6124. And so now we know that from the observation that in some massive clusters, color magnitude diagram can split into more than one isochron. And of course, so here you can see a plot showing the second generation fraction as a function of cluster mass. And from y-axis, we can see that the number of second generation stars changes between 0.2 to 0.8. It shows that the number of second generation stars is not negligible. And of course, we can see a strong correlation between second generation fraction, and of course, and initial cluster mass, actually estimated initial cluster mass. And from observation, we can found another correlation between maximum helium enrichment, so in cluster with the multiple stellar population as a function of cluster mass. Now, we know that all global cluster in Milky Way and some in nearby galaxies show such anomalous abundances in light elements. And so we know that, so actually global cluster or multiple stellar population, not a simple stellar population that we, as people think before, thought before, sorry. So let's move on to the next part of my talk with a question: how are such strange population forming global clusters? To answer this question, some scenarios have been proposed. For example, AGB scenario, fast rotating massive scenario, and so on. And so in most of them, a mix of gas enriched by the ejecta from first generation star and the pristine gas in the ISM formed the second generation star. But in my talk, I will focus, okay, let me say that there's many problems with all of these scenarios, and none of them have been able to explain the observation. But in the rest of my talk, I will focus on HB scenario. And here you can see some actually different stage of HB scenario. At first generation stars form from a cloud with normal chemical composition. And after a few million years, type 2 supernovae of first generation stars expel the remaining gas and stop star formation until about 30 million years. And 10 million years later, the ejecta from HB stars is retained to the cluster, and of course, over the same time period, the pristine gas on the ISM can be accumulated, can be created into the cluster. And from this processed, I mean HB ejecta, and unprocessed, I mean pristine gas. These unprocessed gases can be accumulated in the center of a region of cluster and can cool there. And then finally, second generation star can form from this mixed gas with different chemical composition. So in HB scenario, you assume that at about 100 million years, star formation stop again, which is the start of first generation type 1 supernovae. And I think Elena, our next speaker, will discuss about this section more and present their nice result. Okay, so as I said, I can't go to the next slide. Oh, yeah. As I said, so as the other scenarios, so in HB scenarios suffer from some challenges. For example, so a very massive first generation star is required to form a massive second generation. And of course, a large amount of pristine gas is necessary to dilute the HB ejecta in order to explain the observation. So in HB scenario, the cluster has to retain its HB ejecta and has to accrete the pristine gas from the ISM. But from previous analytic study, we know that the cluster can accrete the ISM gas if this relation is satisfied, and if the cluster and the cluster can retain its HB ejecta if in this condition actually. But let's see what the simulations are. So in 2019, Kalura and his colleagues presented the first set of 3D high-dynamic simulation with Ramses code to study second generation star formation based on HB scenario. They took a very massive cluster of 10 to the 7 solar masses with two different ISM densities, 10 to minus 23 and 10 to minus 24 gram per cubic centimeter. And I will refer these two simulations in my talk to high density and low density simulations. And they found that such a very massive cluster such a massive cluster is able to retain its AGB ejecta and of course can create the pressing gas, and of course finally can form a very massive cluster, very massive second generation cluster, as you can see here. And but we know that the global cluster with multiple population are estimated to have initial masses less than 10 to the 7 solar masses, and so we thought that maybe a parameter study on the cluster mass is useful to investigate. And so in the current study we expand the work to a range of initial cluster masses. Zero of result. So we start with the same setup as their paper, and consider the cluster mass to be 10 to the 6 and 10 to the 5 solar masses with these different ISM densities. And from those analytic estimation, we expect that only the massive cluster of 10 to the 6 solar masses can form a massive second generation. So we now know that. So our result confirmed this prediction. Here you can see some snapshot of a simulation with these parameters. And so here the white contour shows the extent of the second generation star at different times. And we can see a tail behind the cluster, which is because the cluster is moving. And finally, in this section, you can see the final second generation cluster. So in the 10 times denser medium, so the tail is denser. First, you can see tail is denser, and a more massive cluster and more extended stellar component is formed. While in the lower mass cluster, the ramp pressure becomes the gravitational potential of the cluster, and as a result, just a low mass second generation is formed at the center, as you can see here. And finally, only massive cluster are able to produce a new massive second generation. And so in this plot, we can see dilution of AGB ejecta in this simulation with these parameters. You can see solid line shows the total stellar mass as a function of time. And we have also divided the total stellar mass into the fraction of second stellar mass from just AGB ejecta and pressing gas with these red dashed line and dotted line here. There's also a line, black dashed dotted line here. It shows the total injected AGB matter. When we compare this dashed dotted line and dotted line, we can conclude that so in this cluster can retain all AGB ejecta, and we can see that most of second generation mass is it comes from just AGB. But in a denser medium, most of stars form from pressing gas. And when we compare these two dashed dotted line and the solid line here, and amount of gas accretion, as you can see here, increased. So in comparison with the previous simulation, and of course, when we check the other models, you can see it's not true in the case of low mass clusters. And actually, we conclude that 10 to the 5 solar mass clusters show a much lower ability to retain and to accumulate the gas to form second generation star.
3 minutes left.
Oh, sorry. And here you can compare, you can see the second generation and first generation profile densities. It seems that second generation stars are more concentrated toward the center, and we can see the same result in the other simulation. which is in agreement, in good agreement with observation. And of course, so here we can compare. So our results. So we can examine that those positive correlation between second generation fraction and cluster mass. So it seems that our high density simulation shows a positive trend between these two parameters, but you know that there's a difference between observation and our high density simulation. And we thought that it's because of the dynamical evolutional cluster, because so our cluster form just in 100 million years of their life, and we are comparing this result with the present day fractions, and we need to take into account dynamical evolution of our cluster for a better comparison. We simply consider an increasing factor for our clusters, just to consider the effect of dynamical evolution, because we know that from previous study that the second generation fraction can be increased over time. And so in the community, increasing factor between 5 and 20 is common to use. And we simply rescale, we simply have rescaled our values by factor between 5 and 20. And we observed and we obtained this shaded line, as you can see here, for our high density and low density simulations. I think that incorporating such a correction gives us a good agreement between our high density simulation and the observation. And we can see another positive correlation between helium enrichment and cluster mass as well here for just our high density simulation. So it shows that our results, actually our results show a further confirmation that the pristine gas accreted by the cluster have a key role in the AGB scenario in order to explain just the observation. I don't know I have time or not, but yeah, here you can see our main conclusion. The second generation star in our simulation are more concentrated than first generation star in agreement with observation. And in the low density cases, so drum pressure is stronger than, and a compact central helium rich second generation stellar component is formed. And in the 10 to the 6 solar mass cluster, sorry, because of this cluster, the gravitational potential can overcome the ram pressure, and more extended and less helium enhanced second generation can be formed. And in agreement with observation, and for the first time, we find a positive correlation between the second generation to total mass ratio and maximum helium enrichment in second generation star as a function of initial cluster mass. Thank you for your attention. If you have any question, I'm here.
Thank you. We do have time for some questions. Anybody got a question? Oh, okay, then I will ask one. So you earlier on showed some simulations that had various different background densities, right? And you showed that for the different cluster masses, you had you had different relation on pristine gas versus recycled gas. And I was wondering how much, you said it depends on the background density, but does that also depend on what you assume about the cluster itself?
Yes, of course. I think our result depends on the mass of first generation stars and of course the ISM density. If I understood your question correctly.
Yes, I think so. Thank you.
You're welcome.
There's a raised hand, Francesco?
Yes, thanks. Sorry, just to add that these simulations, one important ingredient which is missing is a stellar feedback. So its importance, of course, is in possibly preventing the accretion of gas from first generation cluster and prevent fast star formation essentially. So this is something which is missing now, but which will be partly discussed in next talk in the form of type 1 supernova. But also it will be added in the future in the form of radiative transfer feedback, which is hopefully will be studied in the next future, let's say.
Okay. If there are no other questions, that sounds like the perfect transfer over to the next talk. So could we swap over to Elena, please? Share your slides. We mostly see your emails at the moment. There we go.
Yeah, I know. Sorry. Can you see?
Yes, now it looks good.
Okay, wait.
Francesca, you still have a hand raised if you want to lower that at some point. Okay, so our next talk will be by Elena Lacchin on the role of type 1A supernova feedback on the second generation formation in globular clusters. If you go.
Okay, thanks. So good afternoon to everybody. I'm Elena Lacchin, and today I'll present my work regarding the role of type 1A supernova on the formation of second generation stars in globular clusters. So as I cannot move the, wait, okay. So as Asiyeh already told us, globular clusters are old and complex stellar systems, and from the chemical point of view, most of globular clusters are monometallic, so the dispersion in the iron over halogen ratio is very small, less than 0.1 dex. But the most peculiar feature regarding globular cluster from the chemical point of view is that they show anticorrelations in their light element abundances. Here you can see some of these anticorrelations, and this discovery is now led to the conclusion that globular clusters are hosting multiple populations. However, we know that generally it is assumed that proton capture reaction in the hydrogen burning at high temperature is causing these anticorrelations. However, these nucleosynthetic processes are happening in different types of stars, like for example, asymptotic giant branch stars, fast rotating massive stars, or very massive stars. And it is already unknown which of them are causing the anticorrelations that we are observing now in globular clusters. However, I will focus only on the asymptotic giant branch ones. So I'll just regarding the AGB scenario, we have that we can speak also about multiple generations, since we assume that the globular clusters are undergoing self-enrichment. So we have a second generation that is formed out of the ejecta of first generation synthetic giant branch stars. However, if we take AGB ejecta only, we are not able to reproduce the second generation abundance patterns that we observed. So we need to add a dilution of pristine gas to this ejecta. Here there is a nice sketch of the evolution of the cluster in the asymptotic giant branch scenario. So we have that here a third generation is located in the disk of high redshift star forming galaxy, and then massive stars start exploding. They create a bubble that create a hole in the disk. Then this bubble blows out, and the ejecta of massive stars are released into space. But then when massive stars stop exploding, the bubble collapses, and an inflow starts in the system. The timing of this inflow of gas depends on the density of the ISM, as you will see later. But one of the leading questions and already unanswered question is regarding the AGB scenario is what has halted the star formation of the second generation. Generally, it is assumed that type 1A supernovae has halted the formation of this second generation after some 100 mega years. Here you can see the results of a one-dimensional simulation. in which type 1a supernovae has assumed to start exploding at around 40 megayears. And as you can see in the model with type 1a supernovae, we have that they found that the star formation rate drops almost immediately. However, we want to know if it is true also in three dimensions, and in particular to study the effects, for example, on the chemistry of this addiction of type 1a supernovae on the evolution. So we started at this time here. So when the system is composed only by low and intermediate first generation stars, the more massive ones are undergoing the AGB phase. And since we are assuming that the cluster is orbiting its host galaxy, we will have an asymmetric accretion of pristine gas. And then to this setup, we add type 1a supernova explosions. Just to give some numbers, we are modeling a globular cluster that is quite massive with a first generation that has a mass of 10 to the 7 solar masses. In the time span we're interested in, so it's around 100 megayears, we have that around 1,000 type 1 supernovae are exploding, and we tested two different values for the pristine gas density, so the ASM density of the galaxy. So it is well known that white dwarfs are the death of white dwarfs when they reach the Chandrasekhar mass after having accreted mass from a younger companion. And we modeled it assuming that for each supernova, a Chandrasekhar mass of metals is radiating into space, out of which 0.5 is in iron. And regarding the energy, we assume that 10 to the 51 ergs of thermal energy are injected in the system. Type 1a supernovae are distributed in time following the Greater 2005 formulation delay time distribution for the single degenerate scenario. And we performed 1,000 realizations of this distribution, and we took the one that deviates less from the mean, that is the blue one. However, the delay time distribution is known to be a very uncertain function, not only for its shape, but also for its starting point. So we decided to perform other simulations in which we delay the Greater 2005 formulation of about 25 megayears to see the differences. Regarding study positions, we distribute them in space following the Plummer profile, and even in this case, we performed 1,000 realizations of this function, and the blue one is the one that we have chosen. Going to the results, here for the low density model, so for a pristine gas density of about 10 to the minus 24 grams over centimeters cube, we have that the inflow starts at around 21 megayears, and it is coming from this boundary here. However, as you will see, the inflow is not able to reach the central part of the system. Here you can see it. And because the supernovae 1A are halting and they are confining it far from the center of the system. And even if you compare with the for simulations without type 1A supernovae, here there is an accretion column. However, we don't have it because supernovae 1A are halting its formation. For the high density model, we have that the inflow starts immediately after the beginning of our simulations. And here the situation is different from before, because here the supernovae 1A are not able to confine the inflow far from the center. And even the accretion column can be not clearly seen, but it can be seen here. However, it is continuously disrupted by supernovae explosions. For the low density case, we performed also a simulation in which we delay supernovae 1A of about 25 megayears. So in this case, we have that the inflow starts before, and then the first supernova explosions start. However, after the first megayears, after the supernova explosions, we have that the inflow is still confined far from the borders, and as in the low normal and the standard low density case. So to answer our leading question, if type 1A supernovae are able to halt the star formation rate in globular clusters, we can say that it depends on the density of the pristine gas, because for the low density models, the blue ones, here we have the model without type 1a supernovae, while the blue and the thick line blue model represent the case with type 1a supernovae. And as you can see, the star formation rate hardly reaches the values in the case without type 1a supernovae, and then after some mega years it drops, and it drops also in the case where we delay, that is the light blue ones. However, in the high density models, that are the red ones, as you can see, there is a difference at the beginning, but then the star formation rate is almost the same after some tens of mega years, and also the cumulative mass that we obtain for the high density model is almost the same as in the case without type 1a supernovae. Coming to the chemistry, just for definition, globular cluster can be divided into two subclasses. Type 1 globular clusters are composed by the bulk of globular clusters, and they are monometallic. But there is also a small subclass of globular cluster known as type 2 globular clusters that show an iron spread, and they have also a very large mass. So going to the distribution of the iron over hydrogen ratio, we have that here. The blue one is regarding the second generation, and while the dashed line represents the third generation composition. And as you can see in all our cases, the dispersion of the iron over hydrogen ratio is quite large, and so in agreement with type 2 globular clusters, in particular for the low and the high density cases. When we deal instead with helium, we have that the low density models. In the low density models, we have that almost all the stars of the second generation are composed by very highly helium-rich stars. So we have that here, this quantity represents the enrichment of second generation with respect to the first generation is very high, and as you can look here, these values are completely not matching the observations. Only in the high density model we are able to reproduce the enhancement that we observe. So going to the conclusions, I've showed that type 1a supernovae are not able to halt immediately the star formation as in one dimension, and their effects varies depending on the density of the ISM. So for low densities, the star formation is actually reduced by type 1a supernovae, but the major effect regards inflow. So type 1a supernovae are halting the inflow, and this actually is required by the AGB scenario to survive. So we end up with an observed helium spread between the first and the second generation. While for the high density model, we have that the effect of type 1a is negligible on the star formation rate. The only effect is on the spread of the iron over hydrogen ratio that is in good agreement with type 2 globular clusters that are a subclass of globular clusters.
Okay, thank you. We have plenty of time for questions. No, that's fine. No problem with being a bit short. We've got a raised hand for Tayson. Tayson, do you want to ask your question? You're muted. We can't hear you, unfortunately.
I can't unmute myself.
Yeah, this was my fault. It's fixed.
Okay.
Okay, so it's a very interesting talk, by the way. So
Thanks.
I had a question about the feedback part. First of all, so you form the stars from, the second generation, and you mentioned that you have included type 1a supernovae, but do you include type 2 from the from the second population?
No, the formation of the second generation is limited to stars that has a mass lower than 8 solar masses. So we are not including massive stars from the second generation. This is because if we include them, there will be an iron enhancement due to their explosion, their productions. So this is actually not observed generally in globular clusters. So it is generally assumed that second generation stars has an IMF that is truncated at around 8 solar masses.
Yes, so I understand that part, but this is more like your input, not rather the outcome of the simulation, right?
Yeah.
So I was basically wondering, if you have some star formation, you're going to get immediate feedback from the stellar population form, and that will reduce the mass of the second generation. So that was my question, but you answered already. And if I may ask one more question, Ricarda. Yeah.
Yes, sure. Please go ahead.
So did you? Well, probably I missed it. But so how did you include the mass loss from the AGB? Did you just dump the mass from the from each star particle, or?
The third generation is modeled as an analytic potential, so we are not modeling every star. This is just in every cell we have that there is a contribution of AGB stars at each time step. We are injecting mass coming from the AGBs.
So we don't have to worry about the wind velocity of the AGB. Is that what you're saying?
No, I mean we have we have considered the velocity, but the velocity is assumed to be small, and so the AGB ejecta are able to be reprocessed and form new stars.
Okay, thanks.
You're welcome.
Thank you. We do have time for some more questions if people have other concerns. Yep, there's another one from Francesca.
Sorry, just to add a bit to something important to the discussion. The formation of multiple populations or generations is a very complex problem, and several scenarios have been proposed. I'm talking regarding the question that Taesung asked about the truncated IMF second generation stars. So this is an input ingredient, let's say an ad hoc assumption that needs to be done in order for the AGB scenario to work, because otherwise the immediate effect would be the abrupt stop of the star formation, and also the metallicity constraint wouldn't work anymore, because of course you will end up with second generation stars which are more enriched in iron than first generation stars, which is not observed in most of the clusters. Anyway, there are several scenarios that have been proposed, and every scenario has got a lot of problems, a lot of tricky assumptions that need to be done. And you can, if you have a look, of course, we don't have time to discuss them here, but if you have a look at the reviews that I can point you to, these are discussed in detail. The AGB scenario, the advantage of the AGB scenario is that it is relatively easy to implement in a simulation, and it doesn't contain too many exotic ingredients. Okay, this one of the truncated IMF is kind of a complicated ingredient, but in general, there are other scenarios which involve the existence of very massive stars, of things which have never been observed, I have to say. Thanks for the attention.
Thank you. Okay, I think that brings us perfectly on time to move on to the next speaker. Thank you, Elena. Which is the last speaker before the coffee break. So
so sorry, it's not the first slide. Yeah, you see my screen?
Yep, that looks promising.
You hear me well? Okay. So thank you everyone for this Ramses user meeting. I'm very happy to be there to present our recent work. Today I will present our work concerning disk formation in massive protostellar clumps. So the idea is to form disk population in a large scale and self-consistent environment, which is part of the work of the ERC EcoGAL. So before talking about our simulation, I would like to make a small brief picture of star formations. It's very simplified, so it's not intended to be very scientific, but I just want to say that so star formation takes place in the molecular clouds, and more particularly the dense regions of the molecular clouds that we call dense core, and they collapse to themselves because they are more massive than the disk mass. And during the protostellar collapse, you have the angular momentum conservation that leads to formation of a disk around the protostar, and in this disk you form the planet. And so the properties of this disk are highly dependent on the initial angular momentum budget of the dense core, and also on the physics that is involved, and more particularly on the influence of the magnetic field. Today, I would like to try to generalize the picture that we studied in the past, which was consisting in investigating disk formation in the collapse of a single core, and we will try to generalize here onto the collapse of multiple cores that are located in the same cloud. And in this case, we will be able to form a self-consistent population of protoplanetary disks. Why do we need to do that? So the first reason is simply that, because the disks are connected to the large-scale environment, so it's very important to take into account all the large scales. And the second important point is that there is a very wide diversity of protoplanetary disks in real life. So here I show you an example of observation of all the disks class 2 from the D-Sharp survey, where you see that there is quite a lot of features in the disks that they are all different, they have different properties, they have different mass and radius. So if we want to have an idea of what makes these disks so different, we need to form them self-consistently within one simulation. This, as I said before, are older disks, but there is also wide diversity in younger disks. Unfortunately, for now, we are still unable to resolve them with such accuracy, which is the same because right now in protostellar collapse calculation, we are not able to integrate the model until the class 2, but we are now able to still measure some properties of the earlier stages of disk evolution. And among these properties, the two main important properties that are measured are the mass of the disks and the radius of the disk. And two things came out of this measurement. So first, that young disks are typically more massive than older disks, and more particularly, they are massive enough to form planets, while older class 2 disks might lack the material to form at least the giant planets. So this indicates that the planet formation would happen quite early during the disk evolution. So it's important to model the very early stages of disks. And another thing is that disks are typically quite compact at formation, which means that there is a process that redistributes the angular momentum efficiently enough so that the disks are small. So now what we want to do is to investigate, as I said before, disk formation self-consistently from the scale of molecular clouds. So this has been started in the past with a few other studies. So there were the zoom-in calculation of Michael Kuffmeyer, where they focused on a few individual objects from the scale of a molecular cloud to the scale of the protoplanetary disks. But these simulations were performed in idle MHD and only, as I said before, focusing on a few individual objects, which is not sufficient to form a population. There was also another study of population formation from massive clouds, but it was performed without magnetic field. And as I said before, magnetic field is important to redistribute the angular momentum during the protostellar collapse. And so for the disk formation, it's really important to include it. So we want to extend these studies to the inclusion of first magnetic field and more particularly non-idle MHD that is due to the low coupling between the matter and magnetic field during the protostellar collapse. And we want to also, sorry about the citation here, we want also to self-consistently zooming into regions where a disk is formed in order to investigate the full population that is formed from the calculation. And for that, we use a classic collapse setup of Ramses, but we have a much bigger cloud than before, which is about a parsec in diameter. It's very massive, 1,000 solar mass. We have included a lot of physics, as I said before, non-idle MHD, but also radiative transfer with FLD and stellar feedback from fully formed stars. So more particularly, we include the luminosity of stars, both internal and accretion luminosity. And once some regions are dense enough, we form disk to track the disk, sink, sorry, to track the disk formation around the sink. And we have turbulence, so that the cloud is collapsing at multiple locations, which forms typically an IMF and disk around all the stars that we found. We have run 3 models. One model with pure hydrodynamics, similar to the calculation of Matthew-Bate. One model with idle MHD. So we consider magnetic field, but the coupling between the magnetic field and the gas motions is perfect. And a third model with non-idle MHD, and we included ambipolar diffusion in this model. And we self-consistently zoom according to the Jeans lens up to 1 AU. So this is an example of snapshot that you can get at large scale. I show you the density, and you see at multiple locations, you have dense regions where you have formed a star and around the star a disk. If we zoom in, we see more and more clearly the disk appearing. It's all these screenshots have been taken at the same time, but they are just zooming, and we see that the disk is really connected to the large scale environment. And if we go to the initial screenshot here, we see that multiple disks are formed in the calculation. So now the game is to detect the disk and analyze the population of disks that we have formed. For that, we will select the stars one by one and try to isolate the disk around the stars. For that, we need first to place ourselves in the co-moving frame of the star in order to try to isolate at best the midplane of the disk. So the idea is to take the star and compute the angular momentum direction in the small regions around the star, which helps us to give the rotation axis near the star. And then we have isolated our midplane, and we can select potential disk material according to some thresholds. First, the disk must be rotating. So we impose the azimuthal velocity to be larger by a certain amount to the radial and vertical component. And also, we need to be rotationally supported. So the kinetic energy due to rotation is associated to be higher than the thermal pressure by the same arbitrary threshold. And then we also select the material that is dense enough to be part of the disk. That helps to remove some of the accretion streamers that are also dense and rotating around the protostar. There will be a quite interesting question in the future is whether this threshold for disk formation corresponds to what is actually observed, because observers don't have access to such quantities. So they basically select the disk according to the flux, which perhaps gives us a different selection as we do. So it will be interesting in the future to investigate that. And there is also some additional criterion to select the disk a bit better, but I won't go into much detail, but the idea is to measure the average radius azimutally to refine the selection. And so once we have detected our disks, we are able to produce the populations that we observe from our simulation and compare them all together. And we also compare them with observed populations of class 0 disks that are the same evolutionary stage as the disks that we have. So more particularly, we have compared our disk with the disk from the Van Damme survey and the Calypso survey. And this is what we obtained. So on the top, you have distribution functions of 3 different quantities. So on the left, you have the disk mass. In the middle, you have the ratio between the disk mass and the stellar mass. And on the right, you have the disk radius. The tricolor red, green, and blue are the 3 models that I presented before. We have also some analytical estimate for the non-idle MHD in black in the radius, and the plain histograms are the observations. So first, what we can see is that the mass of the disks are mostly comparable for the 3 simulations and quite in agreement with observation. Also, it's clear that the statistics is a bit insufficient for both observations and theory, but we are in the good range, and more importantly, most of our disks are massive enough to form planets because they lie above the minimum solar mass nebula, which is historically the threshold for needed to form a solar system, but it has been even downward revised in later studies, so we can even push the limit a bit more to the left. So it means that our disks are mostly massive enough to form planets early on. We also see, sorry, that the ratio between the disk of the star, the mass of the disk and the mass of the star, sorry, are comparable for the non-idle MSG and hydro model, but lower for the idle MSG model. So the reason behind that is first because magnetic braking prevents fragmentation, and so the stars are typically a bit more massive in the idle case, and also because magnetic braking reduces the mass of the disk. So you have more massive star and lower mass disk in the idle MSG case. This is why this peaks a bit to the left. And then I would like to talk a bit about the disk radius. So we can see that in the non-idle MSG case, we form a larger population of small disks than in the two other cases. And this is mainly due, again, to the magnetic braking, which, as a difference of the idle case, in the non-idle MSG case, there is something to compensate for the magnetic braking at high density, which is on bipolar diffusion. So small disks can form because of magnetic braking, and they are more stable because bipolar diffusion prevents further magnetic braking at high density. So we have a larger population of small disks in the non-idle MSG case. Here, I just wanted also to present a few scatter plots that I think are interesting. So first, it's quite obvious here that the disk radius and the mass of the system have a correlation. There is a big spread, of course, because other quantities affect the disk radius. And we can see also in this plot that we do form a bigger population of small disks in the non-idle MSG case. There is a minute
warning.
Yes, okay. Sorry, 3 minutes? Yeah. There is also a dependence of the radius of the disk with the vertical component of the magnetic field, which is expected from the magnetic braking theory. We have when we have a stronger vertical magnetic field, we have a smaller disk because the magnetic braking is more efficient. So just before going to my conclusion, I would like to show a bit of fancy stuff, which where we can see that our disks show quite a lot of features, and I think that these features resembles quite a lot the features of older disks. So of course we don't see all of them because first we don't have planets, which is obviously probably very important for the features of protoplanetary disk, and the second point is that we have younger disks. But I think it's interesting to see that our disks, so they are very various in terms of features, and they show intrinsic properties. For example, we see streamers that are often observed in young objects. These streamers are the preferred locus of accretion onto the disk. You also see quite a lot of binarities in the disk, and also sometimes even a more complex interaction where a lot of stars can be in a very close environment, and it often leads to the destruction of a disk. You also see some fragmenting disks when the disks are massive enough. They can fragment into spirals, and sometimes even leads to the formation of a second disk star system. And we also see quite a lot of flybys when you have two objects that fly really close to each other, and this has a strong impact on the disk properties afterwards. You can truncate the disk when you have a flyby. You can see it quite clearly here. Some material is actually taken away from this disk and given to the other disk. So I would like to make a small takeaway message here. So in these simulations, so first, the most important point, I think, is that we are able now to form disks as a self-consistent population from a single calculation. And this calculation can be compared with observed population of protoplanetary disks, and we intend to expand a bit more our parameter space exploration. We have found in this calculation that magnetic fields tend to produce more small disks, and it's actually even worse than what I showed before, because actually in the magnetic field case, we actually remove quite a lot of disks because they are so small that they dissipate at the grid scale. So we have 3 times more disks in the hydrodynamical case than in the non-idle MSG case, which means that probably we need an even bigger resolution to follow this disk, but also then the disks are even smaller in the magnetic field case than we believe. We also form quite a lot of features in our disks that are quite representative, I think, of older disks. And you will be soon able to play a bit with the disk because we are going to make them available to the Galactica database that is developed by Damien Chapon here. And you will be able to access first catalogs of disks and also many plots around many objects. And we sometimes also you will be able to perform post-processing using rotative transfer tools that will allow to do synthetic observation of these disks. So stay tuned for that. It will come in the near future, I hope. And I will leave you with what's next. I think that's reasonable.
Thank you, Ugo. Do we have any questions? Okay. Oh, Tyson again. So Tyson, you go ahead first. Once someone
if nobody raised their hand. I'm not an expert in this field, so but I still wonder. You are zooming into really small structures. So, and this is typically what we have in cosmological simulation as well. And I was wondering, how much of the fragmentation is real, and do you have some idea? Probably you have tested something on this.
I didn't hear the last part. Sorry.
Yeah. So is there any way that you make sure your disk is artificially fragmented or not?
We verify with the GENS lens, and there is a criterion to prevent artificial fragmentations. So as long as you have more than 8 points per GENS lens, you prevent artificial fragmentations. In theory, of course, but in practice, it's the only criterion. But we try to have as much point per GENS lens as we can to prevent that. Yes.
Okay. Yeah, I was basically asking because some people say we should have at least 64 cells to resolve the GENS lengths, right?
Yeah.
So. Yes,
it depends also probably on the temperatures, because if our disks are hot, they will fragment less easily, I think. And in our case, all the disks are quite hot because we have feedback, and I don't think fragmentation is such a big deal, but it's probably, I mean, it would be nice to try to increase a bit the resolution. To see if it affects with the fragmentation, yes. But it's hard to go further for now, but we'll try.
yeah, I can imagine. Yeah, thanks.
Ali, you also had a question.
Yeah, it's just following up on what Tae-sun said. So the GENS refinement criteria is obviously good as the thing is collapsing, but it doesn't really discuss what happens to the fragmentation of the disk after you've reached the maximum level of refinement, and then it's evolving from there. So do you think that the feedback that you have in there is satisfactory enough in order to prevent it once you've hit the maximum level? Or do you think that the dynamics are then problematic at that point?
I cannot really say for sure that it's that we want to prevent fragmentation. I mean, we want to prevent numerical fragmentation. That's for sure. And in this case, feedback seems to be efficient at removing fragmentation. I didn't see very much fragmenting disk. In fact, most of the time they start to fragment into spirals, but that is definitely a real effect, because the disks that are fragmenting are typically the biggest disks. So first, they are very well resolved in comparison with other disks, and the second part is. I don't remember what I was going to say, but yeah, no, definitely. I think it's there is not much artificial fragmentation. Okay, so, yeah. But feedback is not there for that. It's a physical effect.
Okay, I have one final, possibly quick question. So in the observations you showed of which I understand are late disks, but they look very isolated, whereas clearly your disks are very embedded in a larger structure. Do you think that's a feature of the observation, or would you expect your disks to eventually decouple from streams?
Yeah, these disks are more isolated, but yeah, it's because they are older. But there is also something else, and you're right to point out that the disks are quite interacting in our simulation. And in practice, we are forced for now to model the quite compact cloud, because for numerical reason, it's still hard to model a more diffuse cloud, because once the disk is formed, the ambipolar diffusion makes the time step drops significantly. And so it's hard to follow desynchronized disk formation. So it's better if they form at a similar time, because it helps to integrate the model for longer time, enough to have a significant number of disks. So it makes also, unfortunately, more diffuse clouds that are a bit more close to the ones that we observe in nearby the solar system, more difficult to integrate, unfortunately. Yeah.
Okay, thank you. Okay, and I think that brings us to the coffee break. So let's all thank all the speakers again.